today's lesson. We're going to be looking at trig ratios today, and we're going to be looking at them in what's called standard position. In this case, we're going to look at trig ratios with an x and a y-axis. So what I'm going to do is start off by rotating the initial arm up to some point up here, and I'm going to give that point some coordinates. Now I'm being very general about it. I'm calling them coordinates x, y. And we're going to call the length of that little, in this case, terminal arm, I'm going to give it length r. Now what I can draw here for our little angle theta, what I can draw is a little right triangle. What I'm going to do is bring a perfectly vertical line straight down from our point xy. That creates a right angle down here, and it also gives us the dimensions of our right triangle. This length down at the bottom here is x, whatever x might represent, and the length of the other side of the triangle is y. So now I have dimensions, all three sides of my right triangle. And so what I can do is I can name all the trig ratios for angle theta. And I think you'll recognize the first three, but then maybe we'll look at three new ones. The sine of theta is the opposite side over the hypotenuse, so y over r. The cosine of theta is the adjacent side over the hypotenuse, so x over r. And the tangent of theta is defined to be the length of y over x, the opposite over the adjacent. You might remember these through a little memory process called SOHCAHTOA. That's very handy to recognize that sine is the opposite over hypotenuse, cosine is the adjacent side over the hypotenuse, and tangent is opposite over adjacent. Very handy little way to remember it. Now here's the new ones I was talking about. We also have one that's called the cosecant of theta. And the cosecant of theta is really the reciprocal of sine. Instead of y over r, it's r over y. Okay, the hypotenuse over the opposite. And for cosine, the reciprocal function is called secant of theta. And so instead of x over r, or the adjacent over the hypotenuse, it's the hypotenuse over the adjacent side. And the reciprocal of tangent is called cotangent. And so instead of opposite over adjacent, it's the adjacent over the opposite. So there you have it. These are the 6 trig functions. And the nice way that we use with standard form, what makes it so handy is we're not really limited to angles kind of between 0 and 180. We can go to any size angle that we want, and there are ways that we can interpret that using our triangular structure. Let me just show you an example of that. Let's say we wanted to interpret something like this. Say we knew that we have a point at -5, -12, and this is a point on the terminal arm. Of theta. Now suppose we were interested in finding, just start off with, let's find sine theta. Now we could find cosine, tangent, any of the trig functions, but let's just start with sine. This point is on the terminal arm. Well, that gives us something to go by. We can make a drawing. So this point is at 5 to the left and down 12, and I'm going to say that that's something like there. So this would be where our terminal arm is, and we have this point. And so when I go to draw the triangle, I'm going, well, this is very strange. I mean, the angle kind of goes like that. There's theta. And I'm going to try and draw a triangle involving theta. Well, I can't really do that, not with theta. Theta itself is actually more than 180 degrees. But what I can do is draw a triangle that is related to this theta angle. And that triangle means I'm going to go straight up to the x-axis and can again construct my lengths. This is a length of 5 to the left and a length of 12 down. Now I'm going to do a funny thing here. Even though length is technically always positive, I'm going to consider, because I've gone to the negative direction with the x here, I'm going to consider that length negative 5, and I'm going to consider the length going down to be negative 12. And I know that's kind of bizarre, but there is a reason for that. Using Pythagoras' theorem in my right triangle, I could find the length of this hypotenuse. So I know that I have 5 squared plus 12 squared has to equal the hypotenuse squared. So a little bit of calculating here. We're going to have 25 plus 144 equals the hypotenuse squared. So we're looking for the square root of 169, which happens to be 13. So a little bit of Pythagoras' theorem, and we have the length of the hypotenuse. Now, again, technically theta is not in the triangle. But if you think about it, the reference angle is. That little angle there can act as a kind of surrogate theta. Okay, the way this reference angle works is pretty much the same way theta is going to work. Okay, that's the special relationship between an angle and its reference angle. Okay, and again, the reference angle is the acute angle between the x-axis and the terminal arm. So this reference angle is in fact going to behave very much as theta would. Kind of a, as I say, a surrogate theta. So now it's very easy to use the reference angle and say, well, the sine of theta is going to be its opposite side divided by the hypotenuse. So it's going to equal negative 12 over 13. And by interpreting this length here as being negative 12, I don't have to go through any process to decide should it be a negative sign or a positive sign, because as we're going to see here, sines, cosines, tangents, they can all be negative or positive, and it's very important to know which it is. This helps us to make a very easy decision. It's going to be negative 12 over 13. If I wanted to, as I said, I could fill in all the rest. If I wanted cosine theta, for example, that would be the adjacent side, negative 5, over the hypotenuse, and so on. Okay, just to continue, tangent of theta is going to be negative 12 over negative 5, and the negatives cancel, so I get positive 12/5. And of course, I can get the other 3 reciprocal trig functions, but I won't bother right now. So this leads us to a very, very important rule. So I'm just going to clear off this and make way to the very important cast rule. Now, as this previous example kind of demonstrated, sines, cosines, tangents, cosecants, secants, cotangents, they can all be positive or negative. So how do you know, without kind of labeling lengths being negative or positive, how do you really know should it be positive or negative? That's where the cast rule comes in. The cast rule basically tells us the following. Okay, I'm just going to draw my quadrants. By the way, the quadrants are numbered like this. That's quadrant 1, quadrant 2, quadrant 3, and quadrant 4. Now what I'm going to do is make a little observation here. And I'm going to do that with an actual example. So let's say I looked up sine of 30 degrees. Okay, I could do that on the calculator, or I could look in some trig tables. But I would find that the sine of 30 degrees is positive 0.5. Okay, so that's an interesting observation. And then I might look at an angle, and I'm going to use the same reference angle here, which is 30 degrees. So I'm going to kind of build this this little angle up here. There it is in quadrant 1. I'm going to build up that same reference angle over here. And the angle that we would actually name here wouldn't be 30 degrees, but rather we would name that as 150 degrees. So I'm going to use the sine of 150 degrees and see what I get. Again, I would look this up on the calculator, and I would find I get positive 0.5. So we've noticed that in quadrant 1, the sine is positive. Okay. And we see in quadrant 2, the sine is positive. Okay, well, let's mosey on into quadrant 3. And again, just for ease of doing the numbers here, I'm going to use the same little reference angle. I'm going to use 30 degrees. Of course, how do we name this angle? Well, it would be 180 degrees plus 30. So actually, this is 210. That puts us in that quadrant. So let's look up the sine 210 degrees. Well, this time it turns out to be negative 0.5. And I've got one last quadrant to check out, and that's this guy over here. Again, using a reference angle of 30 degrees. And again, we don't name it and just say, well, kind of 30 degrees down from there. We start here and we swing counterclockwise. So that would be 330 degrees. That gets us over here. So the sine, 330 degrees, again using the calculator, we would find out is negative 0.5. So we make a very interesting observation. Sine seems to be positive in quadrants 1 and 2, but negative in quadrants 3 and 4. Okay, we could take any angle. I could take 20 degrees and work my way through it, and I would find exactly the same positive and negative results. So that's how it is for sine. We could go to the drawing board and we could do the whole thing with cosine, and we would get positives, negatives, and so on and so forth. We could do the same thing with tangents. What I'm going to do is summarize the entire results now with our friend the Castro rule. And here's how the Castro rule looks. When I summarize it all very quickly, what do I get? I get this. C, A, S, and T. And what it tells us is the following. Maybe we'll start in this quadrant over here. Any angle between 0 and 90 degrees, any angle, falls into that category. If I look up the sine, the cosine, the tangent, cosecant, secant, or cotangent, I would find that they are all positive. So the A means all angles between 0 and 90 have a positive trig ratio. However, when I go into quadrant 2 and the angles range between 90 and 180 degrees, then it turns out only the sine and its reciprocal, the cosecant, only those two are positive. The rest of them are going to be negative. When I mosey on into this third quadrant and I have angles between 180 and 270 degrees, turns out only the tangent and its reciprocal cotangent are going to be positive ratios. And finally, between 270 and 360, only the cosine and secant are going to give us positive trig ratios. So what the Castro rule does for us is it tells us which trig functions give positive ratios. And at a glance, we can tell. Now you might say that that's interesting, but really not very important to me. But let me just show you that it is a very important little rule. What I'm going to do now is do an example, and I think we might just have enough room here. And what I'm going to do is try to solve the following, where we have the cosine of x is equal to 0.8. And we're going to put a little restriction here. We're going to say we'd like to try and find out what x is, what kind of an angle produces a cosine that's going to be equal to positive 0.8. And we're going to say, well, only those angles that are between 2 pi and 0. Now, this gives us a little more information than just there's a restriction on the domain. This tells us, because we're going from 0 to 2 pi, that we want our answer in radians, not degrees. So that's a very important observation. When you see this kind of restriction, we know they want the answer in radians. If they had wanted degrees, if that's what we were after, we would say 0 degrees to 360 degrees. But that's not what it says. So it's radians. So you've got to take your calculator. You've got to make sure that it's set to radians. Okay, so very important, you make sure you're working in radians if that's the kind of answer that you want. And the first thing we're going to have to do is try to get the calculator to help us look up one of these values for x. So we use a little trick. We're going to use inverse functions. And remember that inverse functions undo whatever a function does. Okay, if a function adds 10, then the inverse function will take 10 away and bring you right back to where you started. Well, these are trig functions. So to undo cosine, I'm going to do cos inverse of both sides of my equation. And I'll show you why that works here in a moment. By doing cos inverse of cos, these two functions being inverses, they kind of kill each other off. And I get x equals. So this is essentially what you're going to be doing on the calculator. You go cos inverse of 0.8, enter, and let the calculator tell you exactly what angle has this particular cosine value. Now if you do that and you're in radians, you should get 0.644. At least that's what I got earlier. So this is one answer that the calculator has looked up for us. And I'm going to draw that in my little picture here so I can kind of see what the calculator is saying. Well, where is 0.644? Well, if we're in radians, then this quadrant ranges from 0 to half of pi. And half of pi, remember, pi is approximately 3.14. If you take half of that, you're talking something around 1.6. So it's a very crude guideline here. I can see that 0.644 is somewhere in quadrant 1. So I'm just going to say, okay, there it is. Now that does make sense, because if we go back to the original statement, we're looking for an angle that has a cosine that's positive. And what the calculator has done is said, yep, in that quadrant, sine, cosine, tangent, all of them are going to be positive. So it looks one up for you and grabs the most convenient one and says, yep, that one is. So that's one of our answers. X could be 0.644. But it's not the only answer. There's another quadrant which has a cosine with a positive trig ratio. So how do we figure out what it is in this quadrant? Well, we use a little trick, and it's all coming back to the reference angle. We use the same 0.644. We construct that in the other quadrant that has a cosine that's positive. And essentially, that's where the terminal arm is going to be. But we can't name it as, well, you start here and you swing sort of negative 0.644 because we're supposed to have x between 0 and 2 pi. So what I need to do is get the coterminal angle that ends up in this location. The easiest way to do that, I find, is to just think a complete rotation is 2 pi, and then I subtract or back it up by 0.644. So what I'm going to do is 2 pi minus 0.644. And I worked that out earlier on the calculator, and you should get 5.64, working to 2 decimal places. And so we believe that within this restricted domain from 0 to 2 pi, that we have found two angles that when we put in those angles for x, take the cosine of those angles, we get positive 0.8. And that's these two angles here. This guy here and this guy here. And there's a really easy way to check your work. All you do is go cosine of 0.644, enter, and hope that you get something pretty close to 0.8. And then try cosine 5.64, hit enter, and hope you get something real close to positive 0.8. And I think you will. So that's where the cast rule and the knowledge of the reference angle all comes together to be of tremendous value to us. Okay, we have one last topic to look at this beginnings of various trig equation solving. And the key word is that the following trig ratios are exact. So these are exact trig ratios. Now some trig ratios might happen to be terminating decimals on the calculator, but I think you will find that most of them are decimals that keep going on forever. Basically not very exact. But there are a few that are very exact. And we get those from two special triangles. The first triangle is very simple. And it looks like this. It is a right triangle, and we make the legs of the right triangle, we give them a length of 1. Using Pythagoras' theorem, we find the hypotenuse would then be root 2. Now this is an isosceles triangle, which means that this angle here and this angle here are equal. And since they're equal and have to add up to 90 degrees, each angle is 45 degrees. And the radian version of this, everything looks pretty much the same, except that 45 degrees is pi over 4. Now this special triangle is very good because it allows us to identify, for example, the sine of 45 degrees as being 1 over root 2. And that's an exact number. Again, the key word here is exact. Yes, you could take your calculator and go sine of 45 degrees and hit enter. But you're not going to get an exact number like this. You're going to get a bunch of decimals that go on and on and on. Not exact. And we could go on and look at something like cosine, and that is 1 over root 2. Tangent of 45 degrees, and that would be 1 over 1, which is 1. And of course we get all of the reciprocal trig functions like cosecant of 45 degrees. Remember that that's really just the reciprocal of sine, so instead of 1 over root 2, it's root 2 over 1, which is just root 2. The reciprocal of cosine, which is the secant function, also going to be root 2. And the cotangent of 45 degrees, the reciprocal of 1 happens to be 1. So that's our first special triangle, very important. The second triangle. This one is constructed from an equilateral triangle. What we do is take an equilateral triangle, and an equilateral triangle has all three sides the same length. And all the three angles are equal, 60 degrees. Okay. Now what we do is we split that triangle in half. So I'm going to just erase the 60 degrees up here, and I'm going to split it down the middle here. And instead of saying that this total length along the bottom is 2, I'm going to say it's 1 and 1. Okay? And I'm going to mark that we now have a right angle. And if I use Pythagoras' theorem, and I'm maybe just focusing on the left of the two triangles, Pythagoras' theorem, well, the hypotenuse is 2. So 2 squared equals 1 squared plus this unknown height squared. I'll just call that x. A little bit of math here. We get 4 take away 1. That has to equal x squared. So the square root of 3 is our missing side. So here we have root 3. Now that's the other special triangle. And there's one other angle that we have here. If the total here was 60 degrees and we've cut it in half, then this angle up here is 30 degrees. Okay? I'm going to make a little room here and write that also using radians. So we only really need the one here. We don't need 2 triangles. So let's clean that away. And we're going to put in the radian equivalent of this triangle. So 2, 1, root 3. Those are the lengths. Now this angle here, 60 degrees, which is pi by 3. And this angle here is 30 degrees, which is pi by 6. And this is a very useful triangle because not only do we get special angles, special ratios for one angle, we also get them for another angle. And that's very helpful. So for example, say I was interested in the sine, maybe I'll use some of the radian measures now. Sine of pi by 3. Okay, well that would be root 3 over 2. And that's an exact number. But I might be interested in the sine of pi over 6, the top angle. So that would be 1 over 2. Okay, and I could keep going like this. Cosine of pi by 3 is 1 over 2. And the cosine of pi by 6 is root 3 over 2. And maybe I'll just do tangent and stop there. Tangent of pi by 3 would be root 3 over 1, so just root 3. And the tangent of pi by 6 is going to be 1 over root 3. And of course, we could look at cosecant, secant, and cotangent. But I think you get the idea. Now again, can't emphasize it enough. Key word is exact. So let me do one example. And what we're going to do is see if we can use a little bit of all the stuff we've learned today and find some exact values for the following. Okay, so the one that I'd like to look at to start us off is I want to find tangent of, say, 120 degrees. And let's throw another one in there. And cosecant of 120 degrees. And I want these to be exact. Okay, so let's see what we could do there. Now, everybody's a little different. I like to draw a picture. Some people don't like drawing a picture, but I really recommend with trigonometry, give yourself a little something to look at. Okay, I'm going to start off and draw our grid and say, okay, 120 degrees, well that swings to be past 90 degrees, so I'm into the second quadrant, and I might have something kind of like that. Now, very important, what is the reference angle? Well, 60 degrees. Okay, so very important observation. Aha! The reference angle is 60 degrees, and by George, I have that angle in one of my special triangles. So let's give ourselves a little room. Maybe we'll draw the special triangle over here. So I have 2, 1, root 3, and 60 degrees is down here. And now it's just a matter of rattling off, based on the triangle, what the tangent and cosecant of 120 degrees or 60 degrees are. So that's kind of like step number 1. Tangent of 120 degrees is in fact numerically the same value as the tangent of 60 degrees. Tangent of 60 degrees is root 3 over 1, or root 3. But stop. Okay? The Castro rule tells us one more important detail. Only sine and its reciprocal are positive in this quadrant. This is not sine, tangent. So it must be negative. Very important detail. What about this other guy? What about this cosecant? Well, let's have a look. Cosecant. Well, numerically, the 120 degrees behaves like the 60 degrees, and cosecant is the reciprocal of sine. So instead of root 3 over 2, it's going to be 2 over root 3. Now, the reciprocal of sine and its reciprocal are positive, so leave it positive. There's our answer. So, combination of exact triangles, Castro rules, reference angles, it's just everything working together like a finely oiled machine. Okay. Well, I think we'll look at one last example. And then we're at the end, or in some respects at the beginning, of this long and winding trigonometric road. But at least for now, we'll be at the end. All right, let's see. In this example, we're given some information. We're given that sine theta is negative 1 over root 2. We're also given some other information. We're given that cos theta is positive 1 over root 2. Now we're going to try and find all possible values of theta. All possible values of theta. So we're kind of doing detective work here. We're going to try and figure out from this clue and this clue what all possible values of theta are. Whatever it is. So let me just start by ruling out some of the quadrants that just don't work. For example, sine is negative. Well, let's fill in our Castro rule here. If sine is negative, I can't be in this quadrant, and I can't be in this quadrant. Okay, so we got 50% of the quadrants gone. Cosine is positive. Cosine positive, can't be in that quadrant. So I know I'm in this quadrant. Now, what's our reference angle? Well, let's have a look. I see some of these dimensions here, these numbers, these lengths, 1 and a root 2. It makes me think of this special triangle. And I think I'm going to work in radians. Pi by 4 is the candidate here. So I'm going to build this reference angle in this quadrant. It's the only quadrant that works, so I'm going to build pi by 4 in that quadrant as a reference angle. So how can I name this angle? Because, again, naming negative pi by 4 is probably not the best way to name it. It would be better if we used its coterminal and positive counterpart. So we're going to go a full swing would be 2 pi, and then we're going to back it up by pi by 4. So let's just simplify this little bit of math here. We have 2 pi, take away pi by 4. I'm just going to make that 2 pi over 1. and make a common denominator. So I'm going to multiply the top and bottom by 4. So what I have is 8 pi over 4 minus pi over 4. And so the coterminal angle is 7 pi over 4. So we're there. As far as radians are concerned, we've got 7 pi over 4. But wait, it's even double underlined. Find all possible values. This is great, but it's only one possible value. And it does work, but it's only one. Okay, I'll need a little room. I'm going to need a little bit of room for this. Actually, it's not too bad. Here's going to be our answer. 7 pi by 4 plus all the possible cycles that could occur. If I took this and said, well, heck, let's swing another rotation. Or another one after that. Or another one after that. Or maybe we'll do a few swings going in the negative direction. So what am I really doing? I'm adding multiples of 2 pi. 2 pi, remember, is another full 360 degrees or a full rotation. And n here could also be a negative number, so that would mean we're rotating in the negative direction. So if you think about it, this gives you all possible solutions. And I'm going to put a little disclaimer here that n is an element of the set of integers. Okay, we're only allowing n to be numbers like -2, -1, 0, 1, 2, 3, and so on. Okay? So that's the answer. This is it. A full, complete list of possible solutions. And with that, I'm done for this lesson. Catch you later.